Hello everyone and welcome to the Game Engine programming series where we write a game engine from scratch. One of the greatest aspects of game engine programming is the fact that there are infinite topics to choose from, and today I'm going to start working on a completely new topic, and that's one which brings us one step closer to actually using 3D objects in our games and being able to display them. And that topic is the asset pipeline, which involves importing content files and saving them in a format that can readily be used by the game engine. Let's have a high-level overview of the asset pipeline. The content that's used in games is in most cases created using a content creation tool. Although game assets can also be generated procedurally, as we'll see later in this video, most of the content in a typical 3D game is created using software that's best suited to create that particular type of content. For instance, Maya, Blender, and 3ds Max are used for creating 3D models and animations, and Photoshop and Substance Painter for textures and images. The list of tools is of course endless, but these are just a few examples. Although the files that are created using these tools can be loaded directly in a game engine, they are in general not in a format that's best for use in a real-time application. And that's where asset import and conditioning come into play, the sole purpose of which is to convert the content into assets in a format that's usable by the game engine. In Primal Game Engine, we will have the following asset types: animations, audio, which can be sound effects or music, materials, which are basically a collection of textures and shader code to be run on the GPU, meshes, skeletons, and textures. Some parts of the asset pipeline are of course used by all types of assets, but the import and asset conditioning is mostly unique for each asset type. Therefore, we need to start with one of these assets to lay out the general path that will be taken by any type of assets, and then we can reuse parts of that asset pipeline. And today I would like to start with the geometry pipeline. Looking at the geometry pipeline in closer detail, we see that the geometry can be imported as 3D models that are created by a content creation tool. And to do that, we will have an importer. And when we imported the content file, we'll send it to processing and packing, which in turn will condition the assets into a format that can be used by the game engine and send it to the level editor so it can be saved as an asset file. But as I said before, geometry can also be generated procedurally, and that's a faster route to set up this whole pipeline instead of writing an importer, because that one is specific for each kind of content file that we want to import. So the whole purpose of this geometry pipeline is to get the raw content and condition it into a brilliant asset that will make our engine very happy to use it. So where I would like to start is to define various kinds of primitive meshes. So I'll start with a plane and then a cube and a UV sphere, which is just a regular sphere, and an icosphere, which consists of regularly distributed triangles, a cylinder, and a capsule. Let's start by adding a new project to our solution that's used by the level editor, and that's a new DLL that we will use for importing and processing the content. And therefore, I'll call it the Content Tools DLL. Because we are using this DLL with the level editor, we just need two build configurations. So I'll set up those configurations here now. We won't have any debug or release builds, and therefore I'll just rename these to debug editor and release editor. And let's get rid of this Win32 platform as usual. I also removed the debug and release builds for Primal Editor because we don't have those build configurations for the editor. And I'll do the same for the engine DLL. Now we can see that we have a DLL here, and then I can set the language version. We use C++17. And the only thing I need to do here is, I think, to just set this additional include directories, because we are going to use headers from the utilities in the engine project. So like we did with engine DLL, you can see here that we have additional include directories, and I'll just copy paste this. By the way, I'm going to use level 4, warning level 4 here as well. So I copied this path and I'm going to put that in content tools. And I think we are ready to start. But first, let's get rid of these files because we are not going to use them. And let's close all these files. So the first thing I'd like to do is to create a common header again that will be included in all the files in this project. And here I'll include common headers from the engine. And like we did for engine DLL, we need to define editor interface macro here. So I'll just copy paste this over. Next, I'm going to add another header for our mesh primitives. Here I'll define an enumeration type that will enumerate the types of mesh primitives that we have. And I'll also define a structure that we can use to initialize these primitive mesh types. So for instance, we can have an initial size and subdivision level for the meshes that we generate procedurally. So we'll here indicate what type of mesh primitives we want to have and how they will be subdivided. So for example, if we want to create a plane, then 2 of these 3 components will be used because a plane is 2-dimensional, obviously. So 2 of these will be interpreted as segmentation in X and Y direction, or along the width and along the length of the plane. Whereas for the cube, all 3 of these components will be interpreted as segments along X, Y, and Z directions. And for some others, only 1 component will be used. For example, for the ecosphere, we only use 1 because that's just a number of subdivisions, as we will see later. The size is the initial size of the mesh that we generate. And for primitive types that have different subdivisions, we can also define a level of detail. So we get multiple meshes for different level of details. Now let's create a function that we can call from the level editor to create a mesh primitive for us. So here we have this function that we can call from the level editor, and we give it the initialization information that's needed to initialize one of these primitive meshes. And the result is returned in this data structure that I'm going to define in a minute. So let's add a header that contains common types for the geometry tools that we will have. So this scene data that we are using here is actually just the result of anything that we import or generate in the geometry tool chain. So here I'll define the structure. And this scene data is just a blob of binary data. And some import settings. So we can have some control over how we want to import our geometry. And then we need to include this header in mesh primitives. And then we can go ahead and define this geometry import settings. The first thing we want to add here is some angle that will dictate how the edges will be smoothed when we import some geometry. I'll go into details of this later, but for now it's just a floating point value that indicates an angle. When we import geometry or when we generate geometry, having normals is optional. We can calculate those normals as long as we have valid triangles for our geometry. Because each triangle has 3 vertices, we can just calculate the normal to the plane of that triangle. So with this setting, we can tell the vertex processing part of geometry conditioning to calculate normals instead of using the imported values, or if we don't have any normals imported, then we can calculate normals anyway. And we can do the same for the tangents. Tangents are just like normals, but they are parallel to the plane of the triangles. And there are also bitangents or binormals, but those we can calculate just by using normals and tangents. In Primal Engine, we are going to use the right-handed coordinate system, which appears to be the most common coordinate system. There are frameworks that use left-handed coordinate system. And the only difference between the right-handed and the left-handed coordinate systems is the direction of the z-axis. So as long as your positive x direction is to the right and the positive y direction is up, then the only difference in left-handed and the right-handed coordinate system is the fact that with the right-handed coordinate system, the positive z direction is coming out of the screen, whereas in the left-handed coordinate system, the positive z-axis is going into the screen. And if you happen to have used a content creation tool that uses a left-handed coordinate system, then we need to reverse the handedness, so the triangles are basically flipped. Some content files can contain embedded textures for 3D models, and they can also contain animations. And with these settings, we can tell the importer whether or not it should import the textures and animations as well. Now we are ready to go here and implement this function further. First, we check if we have valid data as parameters. And now we need to create a scene. And this scene is not the same as we have in the level editor. The scene is just a collection of all objects present in a content file that we are importing. Although we are not importing a content file right now, we will be using this scene to use the same data structures everywhere. So the scene is a collection of all the geometry that's in a file. Let's define that here in geometry header as well. So a scene has a name and an array or a list of LOD groups, where LOD stands for level of detail, is a group of meshes that represent an object and all the level of details in that object. So this LOD group contains a list of meshes, and these meshes define what each level of detail of this object should look like. If you would look at this game character, the farther this game character is from the camera, the more pixelated the rasterization of that game character will be. So we can see that here we have 4 levels of details in how far this character is from the camera. And when we look at the meshes in each level of detail, we can see that we can have like 3 different meshes for the highest detailed model. So the designer of this character would like to use 3 different materials for the face, the body, and the helmet. And if this character is a bit farther from the camera, you can see that maybe we would like to use 2 different materials because the face doesn't really need that much detail anymore. And the next step would be maybe a model that has less details on it. As you can see from this outline of this character, it's less detailed. And finally, when the character is quite far from the camera, maybe we don't even want to use 2 different materials. Maybe it's just the head of this character textured over a solid opaque 3D model because we couldn't really see any difference between a transparent and a non-transparent object when this object is that far. So this is the purpose of the list of these levels of details that we have here. This is just a flat list of these meshes, and we will give each mesh a level of detail ID so we can assemble the meshes together later on in the level editor when we want to save them to the file. Now let's define what we want to have in a mesh. The mesh in the context of geometry tools that we have here is just a big scratch data structure that we will be using to put our initial, intermediate, and final data in it and transmit it between the different stages of the geometry processing pipeline. Here we have arrays of positions of the vertices that define the shape of the primitive. And we put a list of normals here and the tangents. The tangents are only needed when we want to do things like normal mapping. And I'll explain tangents later when we use them. But for now, I'll just put the list here, an empty list, because we are not doing anything with it yet. And we have UV sets, and each UV set contains the list of UV coordinates. We have a list of UV coordinates because we could, in theory, have multiple UV sets. But for now, we only use one UV set for the primitive meshes. Later, we will have intermediate data and output data, which is the result of our vertex processing. So now that we have these data structures, we can use them in constructing mesh primitives. I would like to rename these files to primitive mesh because I'm using primitive mesh everywhere as data names. So let's rename this as well. And we need to turn off the precompiled headers for this project. Now for each type of primitive mesh that we have, we need to have a function that would generate that type. So here I'll have a new function pointer type, that's a primitive mesh creator. And that would be any function that takes in a scene, a reference to a scene, and a primitive initialization information. And then we could just define functions that have this signature for each type of primitive mesh. And then we'll have an array that contains pointers to these functions, or an array of function pointers. So this static assert ensures that we write functions to generate each type of primitive mesh here. So as you can see, when I don't include the last one, then this static assert gives an error. And this is where I'd like to stop for now. Today we started setting up the foundations of the geometry pipeline and defined the good part of the data structures that we need to handle geometry, whether it is imported or generated. Next time I'll continue with these creation functions and we'll write the function that generates a plane so that we have something to process in the processing stage. I hope you liked this video. Literally the button down there, please click it, and also feel free to leave a comment if you'd like to recommend these videos to others with the same interest. Then your subscribing, likes and comments would help a lot. And other than that, I hope to see you all next time. Thanks for watching. If you like this video, please feel free to like and subscribe. If you join me on Patreon, you'll get access to the code on GitHub, so you don't have to type everything over from the video. Plus there are also other nice goodies and rewards exclusive to my Patreon supporters. Please use the link in the video description to check them out. I hope to see you next time. Until then, take care and happy game engineering!